New unit, chapter 3,
okay.
current electricity. So till now we have been studying a static charge which just does not move. In this chapter we will study the charge that move, that constitutes a current. So we already know that moving charge constitutes current, and the current is the amount of charge traveled per unit time. I is dq by dt. I is the current, which is dq by dt, or q by t. This is measured in amperes. This is coulombs. This is second. Ampere is basically coulombs a second. All right.
Yeah.
So this is where it starts. Now you might know already. So q is what? Is the movement of, q is the charge, and the charge that moves is the electron only,
Okay.
because positive charge stays inside and only electrons revolve around, so they only move, right? So if you have a wire and the current flowing in this direction, so we say this is the direction of current,
Yeah.
but electrons would be flowing in the opposite direction.
Yeah.
This is called the conventional direction of current, in which current flows, and this direction is opposite to that, is the direction of movement of electron. So q is equal to ne. Okay.
Yeah.
Q is equal to ne, where n is the integer from 1 to up to infinity. It can be anything, the number, right? E is the charge on one electron, so that constitutes the total charge on an electron inside a wire.
Yeah.
Similarly, we can find, for example, the time period of a revolving electron in a circle of radius r. In a circle of radius r, we want to find the time period of an electron revolving in this orbit. So how we can find that? Time is distance divided by speed, or so distance is the distance of this circle, one circle, the circumference from, so for example it starts at this point A and then it comes back at this point, so that will be the distance 2 pi r divided by distance by speed or velocity, the velocity of electron. This is the time period, and the frequency would be, which is mu, with the inverse of time period.
Okay.
This is just the start. Now how do you maintain a steady current in a circuit?
Wait, what is this V?
Nu is this, not V.
Yeah.
This or this? It's this one. This is nu, symbol, frequency. Frequency, this is frequency, is always 1 by t.
Okay.
Now how do you maintain a steady current in a circuit? Like we want the current for a large amount of time. So this is similar to as that of a water pump which supplies water to a tank. All right, let's see figure 3.4.
Point four. Yeah.
So in this figure, as you can see, there is a water pump. This is a water pump.
Yeah.
This is the pipe which supplies water to a tank.
Okay.
This is a tank, let's say at some height. Let's say there is another tank from which it has
Yeah.
extracts water. This is water filled in, and then this pump, this is a pump which pumps up water all the way to the top. This is the ground here, and then this will be the height of the tank. So in order to maintain this, now suppose you also have a opening at this point in the, have an opening in this tank, you can get the water out, right? And then you put it in back like this.
Oh.
Okay,
Yeah.
so this process cannot continue on its own, like the process of filling of water here and then coming to the ground, because you need something here to push water again to the
Yeah.
top. So that's what pump does. It is a source of energy, right? That drives water. And this can be resembled as a some sort of a circuit. For example, like you have a battery or a cell, and you have a wire, you have bulb. So this is a circuit is
Yeah.
completed. This can also be assumed as that of a circuit. So this starts from here, it goes like this, and then it comes back this back into the lower tank.
Yeah.
So this won't do it automatically. You need to push it with the pump, and this pump is analogous to this cell or a battery,
Uh-huh.
which has some EMF or voltage, right? It
Yeah.
has some
What's the full form of EMF?
EMF is electromotive force.
Oh, yeah. Okay.
It has some energy inside. So the same happens in a real circuit. As soon as you uh, connect something to a battery, right?
Yeah.
Now, for example, you see this figure 3.6. So this is the diagram of a battery. This figure 3.6. It has a positive terminal and a negative terminal. So it has chemicals inside it, and due to certain chemicals reactions, a force, which is electrostatic force, which is exerted on the charges of the electrolyte.
Okay.
There is some chemicals inside that. Okay, so if you draw a cell or a battery, so this is the positive terminal, and this B the negative terminal of this. There
Oh,
is
is this where electrochemistry plays its part?
I'm bad at chemistry. Horrible. I don't.
Okay.
Although I good in physical chemistry, but that's something 2 3 chapters.
Yeah, there's only two chapters.
So that only I know. I don't know anything in organic.
I hate physical chemistry.
Physical is the easiest of them all because, but then there are only 2 3, maybe 4 chapters.
Yeah.
We cannot fetch many much marks. Most of that is organic. Anyway,
Yeah.
so this is a cell, and when you have chemical reactions inside it, a force is exerted on the charges of the electrolyte. So there are two types of charges in the electrolyte, as usually an atom has, so positive and negative.
Okay.
So this force, whatever it is exerted inside, that drives positive charges towards the A terminal
Okay.
and negative charges towards B terminal. That is
Okay.
called as Fe, electrolytic force, or
Mhm.
presented by Fe. It is in this direction, Fe.
Yeah.
Alright. Now, as the charge build up on the two terminals, like A has some positive, B has some, okay. So the electric field is set up because whenever you have isolated the charges, it's natural
Yeah.
there will be some sort of field in there. So
Yeah.
an
Yeah.
electric field is set up, and that's called Fe. Okay, that is that field of force.
Um,
Fe is Q, all right, Q into E.
uh-huh.
This electric field was responsible for this force
Okay.
that caused plus and to accumulate here and minus here. And now
Okay.
this field exerts a force on the charge Q, isn't it? Whatever the charge Q we have.
Yeah.
So, for example, we have some positive charge. Now, this field will exert a force on charge Q in the opposite direction of Fn. So, there is another field Fn. Okay,
Okay.
Fn is the force on the positive charge. Mm, because here we have positive, right? So, Fn
Yeah.
is this force. That means whatever the direction of force is, the positive charge will get driven on that side, isn't it?
Okay. Yeah.
So all positive charge gets driven on this. Now the work done, because whenever there is a force, so work done by non-electrostatic force during the displacement of charge. Suppose we want to displace the charge. This charge was
Okay.
displaced, some charge was displaced from B to A, right?
Yeah.
So there was some force involved in there, and that when that happens, the work was done. That work would be, work is force into displacement, right? So
Yeah.
Fn into the displacement that it was. This is the work done. That's it.
Okay.
All right.
Yeah.
So this work done, if we want to calculate work done per unit charge, that is called as EMF. Let's draw a different symbol for it. This EMF.
Okay.
All right. Even this would be epsilon naught. That's, and usually this is
Okay.
EMF. EMF, as you can see, like in general terms, you can say it's a source, or all right, like that of a pump. It has It has some energy inside it which it can supply to the circuit, right, in simple way.
Okay.
So do not worry much about it now. Let's recap something that we studied earlier. Ohm's law.
Slow.
Ohm's law says that V is directly proportional to I,
Uh,
so that V is equal to IR, where R is what? R is the
resistance.
resistance of the circuit. There is an opposition to the flow of electric current, which is denoted by this R.
Yeah.
Now this R is dependent on many things, right? So,
Yeah.
but now before that, let's first draw the graph of V versus I. So how would a graph look like? If
It
we
will be a slow.
would be a straight line like this, something like this,
Yeah.
because it's y is equal to mx, right? That
Yeah.
straight line equation. Now this resistance is SI unit is what? Ohms.
Yeah.
OHM is the symbol,
Yeah.
and this is R. R is V by I. We can say volt per ampere. All right. So what we say when we call something has a resistance of 1 ohm? 1 ohm means that 1 volt upon 1 ampere, right?
Ampere. Yeah.
This is 1 ohm. So one resistance of a conductor is 1 ohm when a current of 1 ampere flows through it on applying a
Yeah.
potential difference of 1 volt.
One. Yeah.
That you already know. The other thing that you already know is the factors. Let's recap that. Factors affecting resistance of a conductor.
Okay.
So resistance of a conductor depends on various factors. First one is the length of a conductor, which is L. So the resistance of a conductor is directly proportional to the length.
Yeah.
Conductor of a small length will have a low resistance, while a conductor with a large length will have a larger resistance.
Yeah.
Correct. But second thing that it depends on is the area of cross section of the. Suppose you take a cylindrical wire. So it has some area of cross section. This is the area of cross section. Now this resistance is inversely proportional to the A. The more you increase
Uh,
it, the less would be the resistance, because the thicker the wire would be, so the lower the collision between the charged particles would be,
yeah.
and then they would be less resistant. And finally, that depends on another thing is the material from which it is made. All right.
Yeah.
So the nature of material of a resistance, for example, copper wire would have a different resistance, aluminium would have a different, iron would have a different resistance, and if you go beyond, like wood would be having altogether different. because that's the
Yeah.
insulator. So the third thing is the material. Now this material, so from this we have seen that R is proportional to L, R is proportional to 1 by A, and if you combine both these two you can say R is proportional to L by A
Yeah.
from first and second.
Yeah.
And if you want to remove this proportionality and introduce a symbol rho to compensate the equal sign, R is rho L by A, it's RHO.
Yeah.
So this is what the material is all about. Rho decides the material, okay?
Yeah.
So this is how you can find the resistance using the length and the area of cross section and the rho of a material. If you want to find rho from here, would that be R A by L?
Yeah.
I've done this because we need to find unit of this rho. It would be how much? This is length, R is ohms, A is meter square upon meter is length. So that would be ohm meter. So SI unit of the rho resistivity.
Yeah.
We call it resistivity. The rho is the symbol, but this rho is called as resistivity of the material or the resistance that we have. It's ohm meters, correct?
Yeah.
Or it is also called as specific resistance.
Yeah.
All right. Now you can see in the table 3.1 the different materials are there and their resistivity is depicted with a value. So silver, copper, aluminium, these all are metals and a good conductor of electricity. So these have a low resistivity and the order is 10 to the power minus 8. Right? The platinum,
Yeah.
mercury, iron. If you move on to the insulators, you can see they have a resistivity which is very huge in order of 10 to the power 10 or maybe more than that.
Yeah.
So lower the resistivity, the good material for conductor is. Alright. So conductors
Yeah.
have very low resistivity and insulators have very large, but in midway you can see they are semiconductors. So semiconductors are those materials which are neither pure insulators nor conductors. They conduct somewhat.
Yeah.
For example, like carbon, graphite, or silicon, these are semiconductors. These have
Yeah.
resistivity that is midway of the two, right?
Wait, is this silicon the same silicon we use for baking?
Baking, you use silicon,
Yeah.
like it is eaten.
Oh, pans. It's like easy. Like it's like a mold. Like you pour the batter in, bake it.
I haven't used it. I don't know what's it.
Like the tin ones. You get tin dishes to
Tin
put in
is
the oven.
tin dishes, like
Okay, never mind.
tin
It's
metal.
okay. Yeah, like metal. When you bake a cake, you pour it into a pan.
Yeah, I've never baked a cake, nor I have seen someone
Oh,
baking one. So I cannot comment on that. Is it some rubber?
yeah, it's like rubber.
Maybe like it's might be silly.
Because you call it, like, we call it silicon stuff.
Anyway, so let us move on. Now we'll find how to find the resistance of a resistor. The resistance is the property of material, but resistor is the physical device that has some resistance. So you might have seen something like this. If you have a charger that is not of any use, you can break it and find something that looks like this. So it has some color lines over it. Follow this is circle cylindrical, okay? It has some lines all over the surface circumference of the
Oh,
cylinder.
yeah. Like, even for laptops, yeah.
Yeah. Mm. So this is called a resistor, and now it has some color code over it, and generally you'll see four lines: one, two, three, and four, and the fourth one will be far apart from the first three. So these codes present the value that is resistance resistor has. For example, it may have a value of 10 ohm or 100 ohm or even 10,000 ohm, whatever.
Okay.
It is not possible to write it on this small resistor. These color codes represent the value.
Oh,
So what do each of these represent? For example, we have four. So first, second, third, and fourth. Now these are colors. Okay, so first maybe red, second maybe blue, and then orange, whatever. But the fourth one is always gold or silver, or
okay.
there is no fourth color at all.
Oh,
But the first three can be anyone from the table 3.2. So the table is black, brown, red.
this is for the first one.
No, just wait, I tell you. Uh,
Okay.
Orange, yellow, and then green, blue, violet, gray, white. This is that. And now each one of these color has a number associated with it. And for example, let's say, okay, so it goes all the way from 0, 1, 2, 3, 4, 5, 7, 8, 9. All right.
Yeah.
Now for the first color, so let us assume, let us say we have violet, yellow, violet, violet, brown, and maybe gold.
Okay.
This is a resistor that, and it has these four colors. We want to find its value that's associated with it. So the first color is yellow. Now move on to the yellow. Yellow has a 4, so 4. Then violet is 7, so 7. And then the third color represents the multiplier. These first two colors represent the number itself. The third color represents the multiplier. That means multiply by 10 to the power the color that it is brown. So brown is associated with 1. So that would be 10 to the power 1. Alright.
Okay. Yeah.
And then this gold is a separate thing. So gold represents the tolerance, like the fourth color represents the tolerance. So this is a multiplier. And the fourth color represents tolerance. See, these are made in factories and it's not possible to make the exact value of resistor, so they may go somewhat here and there. For example, 45 ohm resistance may have a tolerance of 5%, 10%, or 20%. These are the most like used tolerance values. So if it is
Okay.
gold, then this is ohms. Okay, so this is ohms. Now when it is gold, so the fourth color will say that this will have a tolerance of plus minus 5%.
Okay.
That means that in original this should be 470 ohms, because if you solve it, it's 470. But then it may go for 5 centimeter up and it may be 5 centimeter down. Alright,
Yeah.
so that is how it works. Like they don't guarantee, they will guarantee this between this limit. It won't go beyond 5% up or down. That's what they can guarantee, but they cannot tell you the exact value, the manufacturers.
Oh.
Similarly, you are given red, green, and then you are given blue, and then no color. So this is a question. I want to find its resistance. First color and the second color represents the number itself. So red is associated with 2, so 2. Green is 5, 5, and multiplied by 10 to the power the color that is blue. Blue is
Six.
6, and it was 6. Plus minus, no color means see gold, silver, and no color. So gold represents 5% tolerance, silver is 10, and no color means it may go beyond up to 20%.
Oh.
20% up or down, maybe expect. And this is ohms. This would be the value. Very easy, right? Find it. Now let us start with the another topic, which is mechanism of current flow in a conductor. Topic is current flow conductor, that is drift, velocity, and time. So to understand this, we consider conductors, because we are dealing with conductors only. So let's say we have a metal, and then the metals have large number of free electrons. We already know that metals have large number of free electrons, right? Their
Yeah.
outer shell has electrons. So at room temperature, everything is, like, what you can say, neutral. atom is neutral when it is just random.
Yeah.
I mean, when there is no field applied or no force applied to the charge carriers.
Okay.
So they are in random motion, like electrons may go from one place to another as they may feel good to like minimize their energy. But room temperatures at the room temperatures they move with a large velocity, and again these velocities are distributed in all directions. Like they may go like this. Someone is going like this, other is this.
Okay.
There is no particular direction of motion of charge carrier. So on average, the number of electrons traveling in any direction. Example, if you consider this direction, so in this direction, on an average, the number of electrons that would be traveling will be equal to the electrons traveling in the opposite direction. For example, let's say we have n electrons and u1, u2 up to un be the random velocity of n free electron. Then if you find the average velocity, no? So
Yeah.
the average velocity would be adding all of these and dividing by n. That would be zero always because they are just equally like, because if one is like this, other would be moving in this way.
Oh, they will be canceling each other.
Yeah, average velocity, because otherwise they would generate a current without anything, right?
Oh, okay.
There is no net flow of charge, that I mean to say. There is no net flow of charge in any direction. But when you apply electric field to a metal, they are the case of a metal only. When you apply an electric field to a metal, right? Now this electric field apply a force on the electrons as well as on the positive charge. So if the direction of electric field is this, all the electrons would tend to move in the direction opposite to the electric field by a force QE, isn't it? F is the force that each electron is having Q charge, or let's say don't write Q, E.
Yeah.
So this would be the force that now all of them would tend to move in the direction opposite to the direction of E, and they would, because this is a force, and force is accompanied by acceleration. In fact, acceleration is a will have a force. What is acceleration? Force upon the mass, isn't it? Mass of electron. Force is AE upon M. Sorry, A is EE upon M. This is the acceleration each electron would be having.
Okay.
And applying electric field means like we have connected it to some battery. Understand?
Okay.
This is the conventional direction of current, and the electrons would be moving opposite.
Yeah.
Now, as they accelerate, because there are so many electrons, millions of electrons, free electrons that are inside this metal, they would collide with each other when they move with so much speed in the same direction, right?
Yeah.
And they collide, and then they again it starts to move because there is continuous electric field that is being applied. Okay, so
Okay.
for example, they will collide and then they will again start moving, and they collide, they stop, and they start moving again, and they stop colliding. So this process is continuous. Okay, so between any two collisions, an electron gains a velocity, isn't
Oh,
it?
okay.
Because the collision slows down its velocity, and then it has to again regain the velocity, and then in the short period of time it again collides, and then this process happens. So if an electron with a with a random velocity u1.
Sorry, what?
If an electron is having a velocity u1,
Okay.
right, and it accelerates for time tau1 before it collides,
Okay.
then the final velocity just before the collision would be how much? U, the initial velocity, plus acceleration times tau,
Yeah.
because v is u plus at. So initial velocity is u, and then it moved for some time tau for colliding again. And just before the collision, the final velocity it would have attained is v1. That's so
Yeah.
that v is u plus a tau 1. Similarly, for n electrons, v2 would be u2 plus a tau 2, and then for nth electron, vn is plus a tau
T.
n. If you find the average final velocity, not the
Yeah.
initial, the final, so v average for each one of the electrons would be the addition of each one of these
Yeah.
divided by n. That would be u1 plus a tau 1 plus u2 plus a tau 2 plus up to
Yeah.
an. So you can see that you would get something u1 plus u2 up to un divided by n plus a common, a taken out common, and then tau 1 plus tau 2 up to tau n divided by n,
Okay.
because this n is distributed,
Yeah.
and then you separated the two numerators. Now if you see this u1 plus u2 plus un divided by n is the initial random velocity of these type of electrons which had no electric field applied to them. So that average
Yeah.
velocity was u1 plus u2 on n, which was 0, no?
Yeah.
So we can say that this is 0 plus a times, and let's say this whole thing is, let's call it tau. This tau is the this whole expression,
Okay.
like this whole expression.
Yeah.
So this is u, sorry, v average.
Um.
This is the average time between two successive collisions, this tau. So this is called average time, because it's average of all, right? So
Yeah.
average time between two successive collisions, and this is called a relaxation time, because there is some sort of relaxation that they get and then again collide. So this is called
Okay.
relaxation time, and this is a relaxation time, and it's very small, of the order of 10 to the power minus 14 seconds. Very, very small. All right.
Yeah.
Now, if you go the previous discussion, so this was the acceleration that an electron would have upon application of electric field. A is the force that it would be affected by,
Experience.
and then divide by m. E by m, right?
Yeah.
Now, if you want to find, for example, velocity from the acceleration, how would you find? See, if the initial velocity is 0, which is the initial average velocity, then final velocity is u plus at, so you can say this u is when it is 0.
Yeah.
Final velocity is just acceleration into time, right?
Done. Yeah.
So in a way you can say this V average, V average is equal to A tau, and you can replace this A with small e capital E by M tau. So E tau upon M, this is a very important formula. This and V average. V average is E tau upon. Alright.
Yeah.
And this is called drift velocity. Okay.
Drift
This
velocity.
V average is called VD, which is drift velocity. Because they kind of drift. The electrons are not getting any way to move directly from one end to another. They are drifting in a small successive steps towards
Okay.
this point from here to here. That's why this is called a drift velocity, which is E tau. You may get questions from it. Alright, very important formula.
Okay.
So now, as we see something more, which is relation between current and drift velocity. This is also a good relation indeed. Relation between the electric field and drift velocity. Electric field and VD.
Okay.
So as you know, E is what? dV by dr, that means voltage upon of the conductor, right? Let us take again a conductor. This is a wire, and we have connected it to a cell or a battery with the help of wire. So this is a positive, this is negative, this is the conventional direction of current, which is I. This is the direction of electrons. This has a length L, and this area of cross section is A. And the electric field, because this is positive, this is negative, this would be the direction of electric field, the direction of
Yeah.
conventional current. So let us say that n number of electrons are there per unit volume in this conductor. Okay, so n number of electrons per unit volume, not the all, not the absolute number. This is per unit volume, the n. And the charge on electron is already E, we all know that. Charge on
Yeah.
electron. We need to find the relation between this electric field and the drift velocity. Okay.
Okay.
So if n is the number of electrons per unit volume, then the total electrons in this conductor would be how much? The n multiplied by the volume,
Yeah.
because this is per unit volume, and the volume of a cylinder is area of cross section into the length. Alright, this is the total number of electrons. Now if you, by this total number of electrons, can we find the total charge? Since each electron has a charge E, then these number of electrons would be having a charge E multiplied by NaL.
Yeah.
This is the total charge. Alright, let's call it Q. Okay. Now all the electrons which enter the conductor at right will pass at the left when they drift, right? They will
Yeah.
move from one point to another, and the time that that they will take is, time is what? The distance that they traveled, which is the length
Yeah.
of the conductor, divided by the speed at which they travel, which is the drift velocity. Okay, because they drift.
Yeah.
So this is the term. Now further, if you see what is I, the current in the circuit is I is equal to Q by T, right?
Yeah.
Q by T. Now what is Q? We've just found that Q is this much. E
Okay.
and A, although you don't need to, I think, remember the derivation. But
Oh,
anyway, we
okay.
are doing it. So T is this L upon VD. And then when you solve it, I is equal to A and EVD. This is also important result. So I is equal to A and EVD. Correct?
Yeah.
So this is what the relation is.
Oh, okay.
Now again, let's not prove it because it will take time. So from this we can also deduce Ohm's law in another way. Okay.
Okay, I'll be back. Just a minute.
Okay, come back. Okay, so there is a small correction actually. Actually, this is the relation between I and VD, not E and VD. This is this relation between current I.
I.
I'm just telling you
Okay.
that we can also deduce Ohm's law from this, and we'll just directly write that R equal to ML upon is NE square law. M is the mass of.
Yeah.
So this is also expression for resistance. The other one is V is equals to IR, isn't it?
Yeah.
Now R is this, so if you compare it with R is equals to rho L upon A,
Okay.
because they both represent resistance, so R is also rho L upon A, isn't it?
Yeah.
Now you can see this is also R, this is also R, that means the right hand side of both should also be equal. And you can see this is L by A here also. And there is this L by A, that should mean that the rest is representing rho, isn't it? Rho is MNE squared tau.
Okay.
This is also one thing that, right? Now there is also another relation between J, sigma and E, just to care of the numericals. Relation between J, sigma and J is the current density, okay? And what is sigma? See, this is resistivity.
Okay.
Resistivity. And if you take the reciprocal of it, so 1 by resistivity is called sigma, which is conductivity.
Okay. Oh wait, what's J?
J, I'll tell you, conductivity, and it is rho, it is sigma, right? So conduct, and its unit would be the inverse of resistivity. So ohm meter is the unit of resistivity.
Oh.
Sigma would have ohm meter inverse, or 1 by ohm, correct? This J
Yeah.
is the current density, current per unit
Current
area,
density. Okay.
the current per unit area. So the relation between the three is J is equal to sigma E, that you should remember, right?
Yeah.
Now from here You've seen that the resistivity is this much, which is m upon n e square tau. And what we know already is the resistivity is some property of material, isn't it?
Yeah.
Now, this resistivity is m upon n e square tau. So as you can see, it depends on the mass of the electrons, right?
Yeah.
And all several factors and the number of electrons per unit volume and the tau, the relaxation time. So these may be different for each of the metals. Maybe tau is different for iron and copper and all of those things, right?
Yeah.
That's about it. Now I think that's enough for today. We can do some questions based on it. I'll give you some as for today.